Welcome back to our series on applied regression analysis. My name is Mark Ledbetter, and this is lecture video 21. We're in chapter 6. This is correlation part 2. So as far as this video, we're going to talk about R squared, and it's the strength of the straight line relationship. And we're going to talk about what R squared does not measure. And this is called the coefficient of determination. Now last time we went over this formula for the sample correlation coefficient here, R, and we talked about an alternate formula using the standard deviations and the slope. And then we talked about some important properties of R, that it's between -1 and 1. It's dimensionless. There's no units. It's independent of units. If R is positive, beta 1 hat is positive, the slope. If R is negative, the slope is negative, and if R is 0, the slope is 0. We can see that pretty easily looking at this formula, right? Because these two quantities are always positive. They're standard deviations. Okay. And we talked about the fact that R can be interpreted as an index of linear association. The more positive R is, the more positive the association. The more negative the association. Closer to 0, there's a little linear association. Now, let's talk about R and the strength of the straight line relationship. So to measure the strength of the relationship between X and Y, let's think of our predictor Y when we don't use X at all. Not using X, we're just thinking about Y by itself. So if we're just looking at Y by itself, the best predictor of Y is Y bar. And there's actually a proof of this theorem in advanced inference classes that can show that it's the best estimator of the mean. And that's talking about the amount of variation in the estimate. So it really is the best estimator we can find. The sum of squares of deviation associated with this is what we see in our standard deviation, right? Our standard deviation of y is 1 over n minus 1 sum of yi minus y bar squared. So we're seeing that portion here. And so that's the sum of squares of y. And we're saying that if x is of any use in predicting y, the residual sum of squares, called this y minus y hat quantity squared, or SSE, the sum of squares of error, it should be less than SSY. Because the distance from y to the line should be less than the distance from y to y bar. And if that deviation from the line is smaller than the deviation from the mean, then it makes sense that our line is better at estimating y. And so if SSE is smaller than SSY, then this equation for the line fits better than our horizontal equation y hat equals y bar. Now, last time we talked about, in the last chapter, we talked about hypothesis test for beta 1 hat, the slope. So the null hypothesis was that beta 1 is equal to 0. So if beta 1 is equal to 0, if we don't reject that hypothesis, then what we say is we use y bar. So if you say if this is 10 and this is 20, then I'd say, well, what's the predicted value, what's the best estimate of y at x equals 10, we'd say y bar, whatever that is. Well, what about at 20? Well, it's still y bar. But if our slope is significant, then we would choose this value, that's hard to see, but this value here for 10, and maybe this value here for 20 that's on this line, this equation of the line. So if the line is significant, we're going to use it as our predictor of y. If x helps at all, then we would use the linear regression line there. Okay. So we can manipulate the R, and we can show that it can be written as the sum of squares y minus the sum of squares of error or residual divided by the sum of squares y, which can then be written using splitting up the fractions with the common denominator as 1 minus SSE over SSY. And this is also called this is r squared, by the way, and this is called the coefficient of determination. And of course, r squared is going to be between 0 and 1, positive 1. And the numerator represents, that's this quantity here, represents the reduction of the predicted error by using x. And basically, this is the explained error, and this is the total error. Okay? So it's the r squared is the proportion of variation explained by the regression equation. So that's really handy, that we just have to square r and we get the percentage of the, or the proportion, if you want to do it as a proportion, of the variation that's explained by the regression equation. So if SSE is 0, then r squared is 1. In other words, there is no deviation from the line. Here is r squared is 1. Here r squared is 1. This is with beta hat positive, and so r was positive. And here beta hat is negative, so r was negative, but the square, it was negative 1. So here r was positive 1. Here r is negative 1. And the points are exactly on the line. So SSE is 0. Then yi is equal to y hat for every observation. Okay. Now let's talk about what r squared, what r does not measure. R squared is not a measure of the magnitude of the slope, right? Because the slope is r, s sub y over s sub x. So r squared doesn't really measure the slope. It's related to the slope, but it's really r and this quantity that measures that slope. It's not a measure of the appropriateness of the straight line model. So here are some examples when r squared is low, and we see that this would basically be a flat straight line, but there's really no association between x and y, so y doesn't change as x changes. Here, we have an association between x and y, but it's not linear. But because of the shape of it, the equation, the model is fooled into thinking it's a flat line. But it's really a nonlinear association. Here's an example when r squared is high. So here, it's a nice linear association. Here, it's not. But because of the shape of this curved line, and we get this nice high slope, and that means that tells us that we'd have a higher value of r, and we'd think that this is a better association, but it's really not straight line at all. Okay, so that's finished those two sections. So that's it for this video. I hope that helps you understand about the strength of the straight line and what r squared and r do not measure. Don't forget to scan your lecture notes by midnight, the date listed in the course calendar. Be neat so you can read them. Update your formula sheet. You saw some new relationships here. Maybe this will help you remember what these things mean. If you have any questions, come to virtual office hours. And if you can't do that, by all means, email me, and we will see you next time.